Welcome back to Module 5. Module 5 overviews and discusses the rigid pavement transfer functions and models and how they were used to design rigid pavements using the Pavement ME design software. We've already discussed the distress and performance measures of CRCP. This specific session, or Module 5.2.3, focuses on the CRCP design strategies and adjusting the design to achieve an acceptable design. There are 5 learning outcomes of Module 5.2.3 on CRCP design interpretation and review of design strategies and features. These outcomes include, first of all, define and locate the CRCP design features used in the software. Identify the types of pavement materials permissible in a CRCP design strategy. Third, illustrate the impact of key design features and input variables on the predicted CRCP distress. Fourth, explain the assumptions used in the CRCP design strategy. And finally, fifth, list the CRCP design features to adjust or change the design to achieve an acceptable design. Before getting into the details of the rigid pavement design strategies and discussing the transfer functions that are used in designing CRCP, there are 2 chapters that include information and suggestions for rigid pavement design. The 2 chapters include Chapters 11 on pavement design strategies, specifically Section 11.2.3 on new CRCP design strategies, and then Chapter 13 on interpretation and analysis of the trial design, specifically Section 13.5 and Table 13.5 in judging the acceptability of a CRCP design strategy. Now we will open the MEPDG Manual of Practice and briefly go through these different sections in terms of what will be covered within this module on rigid pavement design. So the MEPDG Manual of Practice, let's first go to Chapter 11. Specifically Chapter 11.2.3 on the CRCP design. So this section gives different CRCP design features. We'll also look at these when we get into the software. The design features that can be considered and used in designing CRCP. The next is we'll look at Chapter 13, basically Chapter 13.5 on the interpretation and analysis of the trial design. So we go down to 13.5, it's judging the acceptability of the trial design, and we'll go down to Table 13-5. Table 13.5, guidance for modifying CRCP design trial designs to satisfy performance criteria. And this table simply provides what a designer can consider changing or altering, adjusting to satisfy certain distresses or other predicted variables like crack width, low transfer efficiency for achieving an acceptable design. Remember, only punch-outs in IRI are actually predicted as in terms of design criteria for the software. However, the software does calculate crack width and low transfer efficiency as well as other variables that the user should look at in defining whether certain adjustments need to be made to the design. So with that, we'll go back to the presentation. and then continue. So we will start with the structural and site features that impact CRCP performance and the resulting design. This is a screenshot showing the folder and tabs for the CRCP design properties that are needed in designing a CRCP. We're going to use the software or open the software to show where the CRCP design properties and other variables are located. So we're going to go ahead now and open the software. And we have basically the software open to continuously reinforce concrete pavements. That's our design strategy. And then, as noted previously in the module, we're going to go down to design properties, where the different CRCP design properties are located. The first is the PCC surface shortwave absorptivity. The default value is 0.85, just like it is for jointed plain concrete pavements. The longitudinal reinforcing steel, the bar diameter, is entered by the user. So this is an entry for the user depending upon the bar diameter to be used. The next is the slab, the base slab friction. The user can either have the software associate a base slab friction coefficient for the type of base that's used, or the user can go ahead and enter a value, what the user believes is an appropriate value for the type of base that's supporting the concrete slab. Normally, it's good practice to simply allow the software to select a base slab friction factor or coefficient for the type of base that is selected. And the manual of practice does include the base slab friction factors for different types of base layers. There can be cases, though, where the user may want to select a different value because of potential debonding in certain areas, or between certain base materials, or the surface of some base layers and the concrete slab. But in general, it's generally suggested to allow the software to select a base slab friction value to be used for the base layer selected by the user. The next is the crack spacing. Is the crack spacing computed using the prediction model? The software does calculate a crack spacing. However, the user also has the capability to enter a crack spacing in terms of inches. The value, generally a maximum value of 60 inches is suggested, but higher values can be used. Also, lower values can be used. Again, it's generally suggested in doing a CRCP design to let the software calculate the crack spacing with a specific design criteria, or for a specific design problem. Next is the percent steel. This is simply the percent steel in the width versus the thickness area of the concrete in percent. The next is the slab curl warp effective temperature. The default value is a -10. This input parameter is the same as was discussed for jointed plain concrete pavements. And then the next is the shoulder type. There are generally 4 different shoulder types: a tied PCC but a separate shoulder, a tied PCC that is monolithically poured. Basically, the load transfer efficiency is greater for the monolithically poured slab versus a tied shoulder, but the shoulder is poured separately from the main slab, and then either a asphalt shoulder and or a gravel shoulder itself. And then the last is the steel depth, or the depth below the surface that the longitudinal reinforcing steel is placed. So that's basically all of the design criteria for or design properties for the CRCP. I'd like to go to the structure and simply go through the different types of materials that are permissible in a CRCP. Basically, they're same as for a jointed plane concrete pavement, and we can use just about any type of materials in our pavement trial structure. We can use our asphalt concrete. It can be a dense graded asphalt concrete. It can also be a permeable asphalt treated base layer. Our library basically only includes the dense graded asphalt, but users can develop libraries for other types of base layers, going from a very fine graded, dense graded layer to an open graded layer that's asphalt treated base layer that's used for drainage purposes. That can be below the surface. We can also have different types of chemically stabilized layers. I'll get rid of that one. And then we can have a cement stabilized base layer. We can also have a soil cement within the same structure of different chemically stabilized layers. And then we can either also have the asphalt or the Portland cement concrete slab rest directly on the subgrade, or we can have a non-stabilized base layer going from A1A type aggregate base, all the way to using millings, pulverized asphalt or wrap material can also be used below the concrete slab. And then also, a permeable aggregate layer can also be used directly beneath the concrete slab. So different types of layers can be used. So with that, I'm going to go back to the presentation, and then we will continue with the presentation itself. So we're going to repeat some of the screenshots that we just showed in the software, but provide a little bit more explanation regarding the help or information that's in the help manual for some of the parameters, not all of them. So the first is the bar diameter, or the longitudinal reinforcing steel bar diameter. So simply, this control allows you to define the diameter of the longitudinal steel, the reinforcement bars. It simply self-explanatory in terms of the bar diameter. The next is the slab or base slab friction value. As we noted before, different types of materials of the base can be used, and this base slab friction coefficient is assigned appropriate for the different base layers. So this control allows the user to define the level of friction at the PCC slab base interface. The level of friction presents is directly influenced by the base material type, as well as construction practices during the concrete slab placement. So the user might deviate from the recommended values included in the manual of practice. This frictional resistance is influenced by material type of the base layer and the minimum, maximum, and mean values of the friction coefficient based on the global calibration performed in the Pavement ME design software. And that table was presented in table 11.2 in terms of friction coefficients for CRCP pavements. So, and this table simply shows the default base slab friction values for different types of base material. Again, it's generally recommended that the mean values in the manual of practice be used for CRCP design. Next is crack spacing. Basically, this control displays the crack spacing, which is the average spacing between the transverse cracks that are formed in the CRCP, mainly as a result of other factors such as PCC shrinkage, the concrete slab-based friction, and then the concrete tensile strength itself. The user can allow the program to calculate the crack spacing, which is generally recommended, or the user can also enter a specific value for some reason that they would like to use. So this option allows the user to select whether you want the software to compute the crack spacing internally, as noted here. And as we mentioned previously when we had the software open, the crack spacing, this option allows you to define the crack spacing as a user. The maximum value recommended is typically around 72 inches or 6 feet. Anyway, it's generally recommended to have the program calculate the crack spacing for the CRCP, because it is dependent on multiple factors and variables. Next is the percent steel. This control allows you to define the total area of the longitudinal steel reinforcing bar expressed as a percentage of the cross-sectional area of the concrete slab, centered by the user. The steel depth. This control allows you to define the depth of the longitudinal steel reinforcement bars within the concrete slab, and the depth is measured from the top of the concrete slab. And then this is the permanent curl warp effective temperature difference. Just as for jointed plain concrete pavements, this input for CRCP describes the combined effect of the concrete built-in temperature gradient at time of set, the effective gradient of moisture warping in the concrete, in other words, dry on the top and wet on the bottom, the long-term creep of the concrete slab, and then any settlement of the concrete into the base. It is defined in terms of the equivalent temperature difference. The Pavement ME default value is a negative 10 degrees Fahrenheit, which was established as the optimum value to minimize the error between the measured and predicted cracking for JP, CP, as well as CRCP, and also to minimize the error between the measured and predicted faulting during the global calibration. So it's not just one distress was used to define the permanent curl warp effective temperature difference. The next is the shoulder type. As we mentioned previously, there are 4 different types of shoulders. This controls allows you to select the type of shoulder for the CRCP, the PCC tied monolithic. This option defines a monolithically placed concrete shoulder tied with bars at the traffic lane and shoulder longitudinal joint. A tied PCC or concrete shoulder but poured separately. This option defines the concrete shoulder separately placed and tied with bars in the traffic lane and shoulder longitudinal joint. The asphalt shoulder should be treated as an asphalt shoulder itself. And then gravel, that should be treated as a gravel or unbound shoulder itself. So with that, now this next section is going to focus on the different types of layers that can be simulated and used in designing CRCP. And then when we had the software open, we already went through this. So again, you can use just about any type of material, base material, under the concrete slab for a CRCP design. And multiple layers of different types of base layers under the slab. So different types of base layers can be used. These can vary from a dense graded asphalt base to an asphalt permeable treated base. And why use an asphalt base as opposed to an aggregate base? Erodibility is very low and for the asphalt base, and it is extremely erosion resistant. It also has very good adhesion characteristics with the concrete slab, and the modulus of the asphalt base is high compared to unbound layers. So the predicted amount of punch outs is generally lower with bound types of bases, especially an asphalt base. So different types of chemically stabilized base layers can be used. These vary from a dense graded lean concrete to a cement treated base layer. The different options in terms of the default layers are displayed on this slide. And as we showed on the software, there's about 5 different libraries for different layers included that go from cement stabilized bases to soil cement, including lime stabilized soil and other types of stabilizers. User can also use a cement stabilized base with a much higher modulus, and then also use a soil cement with a lower modulus compared to the cement stabilized base as part of the design simulation or design structure. Different types of non-stabilized or unbound aggregate base layers can be used. These vary from a dense graded aggregate base to an open graded aggregate base used for drainage purposes. Also, millings and pulverized asphalt, as well as pulverized concrete, can also be used as a base layer beneath the concrete slab. These types of base layers are simulated as an unbound layer. The user should use judgment in deciding whether the material will behave as a bound or unbound layer in the structure. This next section of the module includes examples illustrating the impact of selected CRCP design properties or features on punch-outs and IRI in some cases. Punch-outs is very sensitive to the PCC layer thickness because it reduces the tensile stress at the top of the concrete slab. Reducing tensile stresses means you're increasing the allowable number of load applications. IRI is also very sensitive to CRCP thickness, but predominantly because of the number of punch-outs is included in the regression equation. And since the number of punch-outs are extremely sensitive to thickness, then IRI will be very sensitive to thickness. The percent of longitudinal reinforcement has a significant impact on the number of punch-outs. As shown on this slide, the green is 0.6% steel reinforcement. The red is 0.65% steel reinforcement. The blue is 0.67. The purple is 0.7. And the gray is about 0.75% reinforcement of the slab. And as you can see, percent effective reinforcement, percent reinforcement, is very significant on the predicted punch outs per mile. So it's a sensitive parameter and one that the user can control. The depth of the longitudinal reinforcement also has an impact on the number of punch outs. Most failures occur at areas where the steel is placed near or below the mid depth of the CRCP slab. The higher the steel is placed, the better the performance in terms of number of punch outs predicted per mile. So the effect of longitudinal reinforcement, this shows 5 inches below the surface in terms of the number of punch outs over time, 4 inches, 3 inches, and then 2.3 inches, which was in the LTPP program for some selected CRCP sections. So depth of reinforcement is important, and it's certainly something that the designer also has control over in terms of the project specifications. The concrete flexural strength or modulus of rupture also has a significant impact on the number of punch outs per mile that are predicted by the Pavement ME software. The graph displayed on this slide shows the impact itself. Increasing the strength or modulus of rupture and keeping all other concrete properties the same increases the allowable number of load repetitions and thus reduces fatigue damage. This will reduce the number of punch outs per mile. However, there is a relationship between the concrete strength and the elastic modulus. Increasing the strength also results in an increase in elastic modulus. As the elastic modulus increases, the tensile stress that is computed also increases. So it's the impact of the modulus of rupture and the elastic modulus is a dependency on how elastic modulus increases relative to an increase in the modulus of rupture for different mixes. The graph displayed on the upper left-hand corner of the slide shows the regression equation or relationship between concrete strength, 28-day flexural strength, and the 28-day elastic modulus that is embedded in the Pavement ME software. So an increase in the flexural strength or modulus of rupture means we're going to have a corresponding increase in the elastic modulus. The number of punch outs per mile basically increases with the lower concrete flexural strength and or lower elastic modulus combination in accordance with the strength elastic modulus regression equation or relationship included in the Pavement ME design software. So the dashed line, the short dashed line shown here has a concrete strength of 650 psi, and the 650 psi corresponds to an elastic modulus just above 4 million. The solid black line has a concrete strength or modulus of rupture of 750 psi, and 750 psi has a modulus of rupture of about around 4.5 million. The longer dashed line has a concrete strength of 850 psi, and 850 psi would have a modulus of rupture of about 5.1 or just lower than 5.5 million psi as an elastic modulus. So concrete strength and elastic modulus are important. Their combined relationship in the Pavement ME, still the higher the strength of the material, even though the elastic modulus is going to increase, the number of punch outs generally decreases with an increase in strength. The type of shoulder also does have an impact on the number of punch outs. The red is an asphalt shoulder. The green curve is a shoulder. It's a tied concrete shoulder, but poured separately. And then the blue is a concrete tied shoulder that's paved monolithically or at the same time as the concrete slab. And so the type of shoulder does have a pretty important impact on the number of punch outs that are predicted. An aggregate base would be, it's not shown on the slide, but it would be much greater than the shoulder for an asphalt shoulder. Much more punch outs would be predicted for the aggregate itself. And this is the effect of base type on punch outs. Not the shoulder, but the base type on the punch out. So the base type has a moderate impact on the number of punch outs. The blue is the aggregate base, and that's a baseline shown here. The red is the predicted punch outs for a cement treated base. The green is also at the same line of a CTB, and the green is an asphalt treated base. So it does have an impact, and the type of base would be controllable by the designer, something the designer should consider. The CTE is normally not controllable by the designer, especially in areas where limited types of aggregates are available locally. However, lower CTE values reduce the curling and warping of the PCC slab or lower thermal movements. Selecting some aggregates with the lower CTE values, even if they have to be imported, can result in more cost-effective designs because of its impact on the number of punch outs per mile. So the purple is a coefficient of thermal expansion of 4, has the lowest. The green is a 4.5. The darker one is a 4.7. The blue dashed is 5. The red is 5.5, and then the purple or the dashed one is a coefficient of thermal expansion of 6. So it does have an impact on the punch outs that are predicted by the software. And as expected, the average annual daily truck traffic has a significant impact on the number of punch outs. Average annual daily truck traffic is something that's usually not controllable by the designer unless the designer is adding more lanes. So the what's shown here, the green has an average annual daily truck traffic of 1,500, the dashed line of 3,000, and the red line is 6,000. So the amount of trucks, as we would expect, has a significant impact on the number of punch outs that are predicted by the software. Also, the effect of reliability on the punch outs. As for most of the other distresses and other pavement design strategies, the reliability does have a significant impact on the number of punch outs, but its magnitude of impact is affected by the standard deviation of the residuals. So the more accurately we predict the outcome, the lower the standard deviation of the residual and the less of an impact of reliability on our final design. So starting with the standard deviations of the residuals from the global calibration, this is an example of the impact of reliability on punch out. So the green is a 50%, that's the baseline, the mean value, 50% reliability. The dashed blue is 75. The red is a 90% reliability. The dark dashed is a 95, and then the 99% reliability is the dashed purple type line. I believe these are reversed on the legend. This is the 99% reliability, the 95% reliability, and then the 90% reliability. So reliability does have an important impact. Okay, in this next section, we're going to discuss some of the important assumptions and things we should remember when designing CRCP. And some of our things to remember and our assumptions are identical to what we've previously discussed for jointed plain concrete pavements. So two important variables that have a significant impact on the concrete layer thickness is the relationship between strength, either flexural or compressive strength, and the elastic modulus. The graph displayed in this slide illustrates that there are relationships between strength and elastic modulus for which the same number of punch-outs will be predicted throughout the design life of the CRCP. In other words, the amount of punch-outs predicted for the 9-inch, 10-inch, and 11-inch CRCP are, as shown in this case, are all 15 punch-outs per mile for combinations of strength and elastic modulus displayed on the graph for the different PCC thicknesses. So, starting with the 9-inch, this shows for a 9-inch CRCP slab, every strength, 28-day strength, and 28-day elastic modulus combination that is consistent with this relationship, we would predict, or the software would predict, 15 punch-outs per mile at the end of the design life, everything else being equal. The solid line is a 10-inch CRCP. And again, for the 10-inch CRCP, this strength modulus combination, in accordance with this relationship here, would result in 15 punch-outs per mile at the end of our design life, everything else being equal. And finally, the 11-inch CRCP, this shows the combination of strength and elastic modulus values that would result in 15 punch-outs per mile at the end of the design life, everything else being equal. So there is this internal relationship between strength and module at which we would predict the same amount of punch-outs for different strength modulus combinations. And that becomes relatively important, especially for agencies or organizations developing catalogs to be used in design. Now, it is important to recognize the regression equation included in the Pavement ME design software for concrete strengths or mixtures exhibits the relationship displayed in the graph by the solid black line. However, the laboratory-derived relationships do not always follow the regression equation. The laboratory measurements of flexural strength and elastic modulus are displayed in the graph by the solid blue circles and short dashed line on the slide. So the solid line is the regression equation that's embedded in Pavement ME, and the user can simply enter a 28-day flexural strength and have the program calculate the 28-day elastic modulus or an elastic modulus. Conversely, the user can enter a 28-day strength and also enter a 28-day elastic modulus. And then the program will use that in calculating the tensile stresses and the number of punch-outs per mile. As displayed, there can be a difference or bias between the regression equation included in the Pavement ME design software and the strength elastic modulus values measured in the laboratory for specific concrete mixes. The laboratory measured values above the solid line, or the regression equation included in the software, means the strength elastic modulus of the PCC mixtures are less resistance to fatigue cracks, or the number of punch-outs in comparison to the Pavement ME design software regression equation, while the laboratory measured values below the solid line, which include most of them, represent concrete mixes that are more resistant to fatigue cracking or the number of punch-outs. And we'll come back to this point again in a couple of slides. This graph, the graph displayed in this slide compares the data or observations included in the previous slides. In summary, the solid black line and a longer dashed black line represent a 9-inch CRCP slab and 10-inch CRCP slab with equal punch-outs predicted at the end of the design life at 15 punch-outs per mile. These relationships between strength and elastic modulus are then compared, or can be compared, to the laboratory measured data and to the regression equation between strength and elastic modulus included in the software that was on the previous slide. Thus, the inputs to be used in design should follow the input level used for calibration. In other words, if the laboratory measured values, the blue circles, were used either for input levels 1, 2, or 3, those laboratory measured values should also be used in design. If the concrete strength elastic modulus relationship embedded in the Pavement ME design software was used for calibration, then that relationship, the regression equation, should also be used for design, because there is a bias between the laboratory and regression equation included in the Pavement ME design software. As such, input compatibility is important because there can be a bias between the input levels for concrete mixes. It is important to know and follow the process and variables used for the calibration process. As stated for the previous slide, if the PCC strength and elastic modulus regression equation was used for calibration, the regression equation used for calibration, then it should also be used for design. However, if the laboratory measured data were used for both strength and elastic modulus, and they were used for calibration, the laboratory measured values for strength and elastic modulus should also be used for design. Remember from Module 4.4.1 on subgrade soils and Module 4.4.2 on aggregate base materials, the resilient modulus of any unbound base layer should be compatible with the water content dry density entered for a specific design. Just like for concrete, on strength versus modulus, we need to have input compatibility for the different layers, i.e. resilient modulus related to the water content and dry density of the material. As mentioned in the MEPDG Manual of Practice under Chapter 3.5, Factors and Features excluded from the MEPDG, durability and disintegration of the concrete layer, as an example, decracking, is not predicted by the software. It is assumed that the concrete materials and mixture will be designed and placed to prevent any durability issue from occurring throughout the design life of the pavement. As mentioned in the MEPDG Manual of Practice, also under Chapter 3.5, Factors and Features excluded from the MEPDG, volume change of the soil in terms of frost heave and or frost susceptible soils, or potential vertical rise from expansive soils is not predicted by the software. It is assumed that the subgrade will be properly treated and constructed so the volume change of the soil is minimized and does not become an issue throughout the design life of the CRCP. Remember, the distress threshold values and or design criteria need to represent the agency's policy of when to rehabilitate or repair the pavement. So these values represent the surface condition that triggers major rehabilitation. The fundamental performance of the pavement is estimated through the calculation of IRI throughout the design life. IRI is heavily dependent on pavement distress. For CRCP, heavily dependent on punch-outs, as well as the site factor for some climates and some soil combinations. Removing and replacing problem soils, such as highly frost-susceptible soils and highly expansive soils, can reduce the impact of the site factor on the increase in IRI over time. This section of the module will now focus on interpreting and adjusting a CRCP design to satisfy the design criteria and reliability level selected by the user. When a trial design does not meet the design criteria or reliability level, what needs to be adjusted or changed to achieve an acceptable design? This section provides some suggestions on determining what input and design strategy variable should be changed in adjusting the design to satisfy the design criteria and reliability level selected. So some suggestions or suggested steps to take, the user should take in adjusting a CRCP design to achieve an acceptable design are going to be mentioned and or discussed with this slide. The first, the user should determine the distress criteria or performance measure that did not pass. In other words, for CRCP, is it the number of punch-outs per mile or is it the IRI? Second is to check the site factors and determine or confirm that they are reasonable and are an accurate representation of the site for the CRCP pavement. The third is simply to check the inputs to confirm they are correct. In other words, we haven't made a blunder as part of the inputs. The fourth is to identify one or more design features that have a significant impact on the values that did not pass. However, it's not suggested that you change multiple design properties or features at the same time unless you're using the optimization feature in the software. It's generally suggested to make one change or change one design property or feature at a time so the designer can understand what impact that has on the distress criteria that did not pass the criteria. And then finally, the fifth is to change one design feature at a time to understand its impact on the trial design. Table 13.5 in Chapter 3 that we looked at in the Manual of Practice provides some suggested modifications for reducing the distress to achieve an acceptable design. It's generally recommended that the user obviously focus on the input parameters that are controllable by the designer and still have a significant impact on the predicted distress. So controllable by the designer and have a significant impact on the distress. This table displayed in this slide simply illustrates the importance of the design factor or feature in changing the distress variable. 3 check marks indicate the distress variable is highly dependent on the design property or feature or factor. 2 check marks suggest the design property has a significant impact on the predicted distress. 1 check mark suggests the design factor or property has a minor impact on the predicted distress. No check mark suggests the design property has relatively no impact on the predicted distress, or its impact is on one of the other distresses. As an example, punch-outs are extremely sensitive to changes in slab thickness. So if the number of punch-outs are predicted to be too high, increasing slab thickness to reduce the number of punch-outs is something a user should consider. Similarly, punch-outs are highly dependent on the PCC strength as well as the elastic modulus of the concrete mix. Punch-outs are also highly sensitive to the coefficient of thermal expansion. Using a lower CTE value reduces the number of punch-outs. The aggregate size has a minor impact on punch-outs. The use of widened slabs has a significant impact on punch-outs and a minor impact on IRI. Now, continuing with the impact of the different design properties as displayed on this table. Increasing the percentage of steel has a significant impact on the number of punch-outs. Increasing steel reduces the number of punch-outs. Reducing the depth of reinforcement has a minor to moderate impact on the number of punch-outs. Reducing the depth of the steel, having it closer to the surface, reduces the number of punch-outs. Using more erosion-resistant base material has a minor to moderate impact on the amount of punch-outs. Using an asphalt base or a stabilized base versus an aggregate base that can be highly erodible would reduce the number of punch-outs. Using tied PCC shoulders has a minor to moderate impact on the number of punch-outs. Removing and replacing problem soils has a low impact on punch-outs but can have a very significant impact on IRI. And then requiring smoother CRCP at the time of construction. In other words, a lower IRI value at construction can have a significant impact on IRI for design. There are other impact variables that have a significant impact on the CRCP distresses, but the designer generally does not directly control the inputs. The permanent curl warp effective temperature difference has a significant impact on the number of punch-outs. The lower the temperature difference, the lower the number of punch-outs. However, the designer generally does not control this variable, with the exception of some design build projects defining whether it's nighttime, daytime type construction, where the temperature difference is trying to be controlled. Traffic volume is not controllable by the designer unless the designer is adding lanes to the project. However, traffic volume has a significant impact on the number of punch-outs. This should be 3 check marks rather than 1. And then the climate and or location has an impact on punch-outs, but also would have a much larger impact on IRI because of the site factor variables that are related to cracking. And then the subgrade type also has a minor to moderate impact on number of punch-outs, but a larger impact on IRI because of the site factor variables that are related to the soil type. And remember, the combination of climate and subgrade soil can have a significant impact on IRI over time. So the designer should not blindly select any CRCP design property or feature to try to reduce one of the distresses or number of punch-outs per mile. Some adjustments that are usually not cost-effective in reducing the number of punch-outs are listed on this slide. Increasing the PCC or the concrete thickness to reduce the IRI is usually not cost-effective. Increasing slab width just to reduce IRI is usually not cost-effective. Also, increasing the percentage of reinforcing steel simply to reduce IRI is usually not cost-effective. So next is a summary of the CRCP design in terms of this module. So we had 5 learning outcomes of Module 5.2.3 on CRCP design interpretation and review of design strategies and features. So the outcomes were, our first one, defined and located the CRCP design features and properties used in the software. The second, identified the type of pavement materials permissible in a CRCP design strategy. The third was we illustrated the impact of key design features and input variables on the predicted CRCP distresses. The fourth, we explained the assumptions used in the CRCP design strategy. And then the fifth, we listed the CRCP design features and properties to adjust or change in design to achieve an acceptable design. In addition to the outcomes from Module 5.2.3, remember from the previous 2 submodules on the CRCP distresses of punch-outs and then IRI, Module 5.2 provided the 2.3 provided the following outcomes, or the previous 2 modules provided the following outcomes. We described the CRCP distress transfer functions for the number of punch-outs. That was Module 5.2.1. We described the CRCP regression equations for smoothness degradation, or IRI, which was Module 5.2.2, and then defined and explained the CRCP design properties and features, which was Module 5.2.3. So this ends Module 5 on rigid pavement design strategies and transfer function. The next module of the training course sequencing is Module 6, which will be an overview of the flexible pavement and semi-rigid pavement design strategies and transfer functions.